We're going to start actually before getting into the talk with an introduction from the director of the Fields Institute, deputy director, sorry, Patrick Ingram, and I will pass you the mic.
Right, thank you. Yeah, I'm Patrick Ingram. I'm the deputy director of the Fields, and I'm glad to be here today. It's my pleasure to a little bit later present the Margaret Sinclair Memorial Award. But I also just wanted to say a few things. I wanted to say welcome to everyone. For a longer event, we have a slide deck that we go through, but I think I'll just sort of, because this is a shorter event, get you to the content more quickly. Most of you know about the Fields Institute, but I'll just mention, if there's anyone new, that the Fields Institute for Research in Mathematical Sciences is the full name, is a center obviously for math research. And it's a place where mathematicians around Ontario, Canada, abroad, and so on, come from academia, business, industry, and so on, and come together to carry out research on whatever sort of questions in math and math education are relevant to us. So our mission is just to provide a supportive and stimulating environment for research in math and in math education. Part of that supportive and stimulating environment is avoiding anything like harassment or anything like that. So if anything at all, at any point makes you feel uncomfortable, you can always come to me, but we also have an anonymous, on the website under resources, we have an anonymous reporting system, which does not get used that much because we do have a very positive environment, but just it's there if you need it. So I will be presenting the award in a moment, but I think first I'm going to pass the microphone back over to Charles to say a few words about the award itself.
Just prepared a few words. So the Margaret Sinclair Memorial Award has been awarded for the past 12 years at the Fields Institute for Research in Mathematical Sciences. And we're coming together to honor the legacy of Dr. Margaret Sinclair, who passed away in 2012. Her contributions as a dedicated and innovative Canadian mathematics educator, which a number of you in this room can still attest to, either through personal experience with Margaret or through the exploratory spirit that continues in these gatherings. This award recognizes early to mid-career educators in Canada who demonstrate excellence and creativity in promoting mathematics education, and it's a fitting tribute to someone who championed accessible and engaging learning for all. Dr. Sinclair's own journey was a testament to her perseverance and lifelong love of learning. Throughout her career, she taught all levels from kindergarten all the way to PhD students, working as a teacher and a vice principal in the Toronto Catholic District School Board, and later as a professor at York's Faculty of Ed. A pivotal moment in her trajectory was in 1988, when she earned her Bachelor of Arts in Mathematics from the University of Waterloo through distance education, all while raising 5 children at home. She continued by completing a master's degree in mathematics for teaching, then earned her PhD from OISE. She then joined the Faculty of Education at York as a professor, where she became a respected researcher and a mentor to many. Margaret organized junior math olympiads, CMESG, OME through the Scarborough chapter, and as attested by one of her advisors, Walter Whiteley, spent her time building communities of people. Her research involved the learning of spatial reasoning in the classroom. She experimented with the use of dynamic geometry software and blended learning to enhance mathematical comprehension. And Dr. Sinclair was known for her talent in designing carefully structured explorations that helped many students and teachers develop a deeper understanding of math through visualization. She firmly believed that mathematics is a beautiful and critically important subject that can be made accessible and engaging for all learners. Dr. Sinclair's connection to the Fields Institute, a leading center for mathematical research and education, was solidified posthumously. In recognition of her significant contributions to the field, she was named a Fellow of the Fields Institute. To further commemorate her impact, the Margaret Sinclair Memorial Award, recognizing innovation and excellence in mathematics education, was established. Her friends and colleagues remember her as a passionate educator with an infectious enthusiasm for life, encapsulated in her motto, "Seize every day." The award in her name continues to inspire educators to embody her spirit of innovation and dedication to making mathematics a subject that is not just understood, but also appreciated and loved. And we're honored today to celebrate Dr. Andie Burazin, the recipient of the 2025 Margaret Sinclair Memorial Award winner for her exceptional innovation and excellence in mathematics education. The awards committee celebrated Dr. Burazin, who works as an associate professor in the teaching stream at the University of Toronto Mississauga, for her impact on creating, organizing, and running vital communities of practice that yield far-reaching outcomes. She's distinguished herself as a driving force in building vibrant and supportive learning communities, and as a national leader in mathematics education. I'm going to say a few more words about her work here. So Andie is a co-organizer of FYMSiC, which we talked about a little bit earlier today, first year in Mathematics and Statistics in Canada project. Initially a forum for educators to address challenges in early university math courses, FYMSiC became an essential lifeline for many during the pandemic, fostering a space to share innovations in teaching, research, and outreach. The initiative reflects Andie's core belief in the power of community for personal and professional development, bringing joy and a sense of belonging to her colleagues. And at the heart of her work is a deep focus on communication within mathematics, understanding and easing the often difficult transition for students between high school and post-secondary mathematics. Her research seeks to identify the origins of learning gaps and to design courses that effectively bridge them. This has led to significant contributions in improving the literature around numeracy, where she strives to reduce ambiguity and find clearer, more engaging language to help instructors teach and students learn. Her influence extends to her work as a co-author and editor of several mathematics and statistics textbooks, and as a researcher on a SSHRC-funded health numeracy project, which aims to create online teaching modules to benefit healthcare professionals and students. For her foundational work in enhancing numeracy through improved communication, her unwavering commitment to building community, and her leadership on the national stage, Dr. Burazin truly embodies the spirit of the Margaret Sinclair Memorial Award. As is customary upon the receipt of the award, Andie will deliver a lecture, which will be followed by a discussion among the forum. Come on up, Andie.
It's my great pleasure to award, give you this envelope as well. Yes, it's my great pleasure to award the 2025 Margaret Sinclair Memorial Award to Andie Burazin for the reasons mentioned by Charles. I'm going to put this down.
Okay, so I guess it's my turn to talk. First and foremost, I feel very humbled to be here today and to actually receive this award, and to be a part of the group of individuals who previously received this award, some of which are my colleagues, Brian Forrest and Ann Kyender, who are on the call with us online. So it's quite the pleasure to be a part of that group, individuals who've actually made great impacts in mathematics education all across from K to university and beyond. I also want to thank the Fields for this opportunity, and those on the committee for selecting me. Thank you. So I appreciate that as well. So just a little bit about me. Thank you for the kind words, Charles. I am an assistant professor teaching stream at the University of Toronto Mississauga. I primarily teach first year and second year calculus courses in the mathematics department, as well as a numeracy course in the Institute for the Study of University Pedagogy. So I get a huge breadth of students that I see every year, every academic year. With numeracy, it's individuals who really have this struggle with mathematics and numbers. The classroom size is about 30 capped at 30 individuals. So it's very different from teaching a first year, second year calculus course where my classroom size is 150. And if I coordinate, there's several hundred students. And so there's a wide variety of individuals that I teach. One thing I want to say, and anything that I say in my presentation, it takes a team to do most of the work that I've been a part of. It's not an individual thing, so I can't take credit for it. It is a team effort, and anything that I have accomplished, I wouldn't be here if it wasn't for certain individuals supporting me, in particular for this award. As soon as I heard about the award, I emailed everyone who supported my application like 5 minutes after receiving the email from the Fields. And then there was a second thought, I have to talk. And I'm one who really doesn't like having attention on themselves. I did think about this presentation for the past few months, and here it is, and we'll get through it, Andie, together. Yeah, so I'm just going to go into an abrupt change because I'm very known for switching over. I'll get to my presentation right now. Okay, so thank you, audience, for coming, and I have several questions throughout my talk where I'm going to ask you to reflect, possibly even answer the question amongst everyone. So I want you to think of one person that you get along with, one person that you get along with. So just take a second, identify that person. It could be a dog, it could be your mom, your best friend, okay? And then think about why you get along with that person. So take a minute, and I'll ask some people to share what's the reason you get along with that person. No. So take a second. So why do you get along with that individual? What are the reasons for you, having that connection with that person? Does anyone want to share? Thank you, Diana. Value similar things. That's great. Yes. Similar temperaments. Yes. To get your jokes. Okay. So there is a common intersection of like beliefs and ideas and interests and whatnot, but I think it goes a little bit further, in my opinion. For any relationship to be successful, I think that there's two things that need to happen. And it's even a relationship when it comes to mathematics, an individual working and thinking about mathematics. It's trust and communication. If you don't have these two things, that relationship, in my opinion, I don't think it will be very successful in long-term trajectory. So the aim of my talk will be on communication. I won't be speaking to trust. I think trust is really important. It's huge. And when it comes to a context of mathematics, it's the trust that your teacher, if you're a student, will guide you through the course, that you're going to learn, that they're not going to mislead you. Or when you read some piece of mathematics, some text, that the author is actually telling you credible information, it's valid, it's accurate, and you trust that what they're saying makes sense and that you're going to learn from it. So trust is important, but my bread and butter of this particular presentation will be communication. Now, I am by no means an expert when it comes to communication. I fail quite often, but I always try and fail and try and fail, and you see my pattern. But it is something that one has to practice, and sometimes it just doesn't work, right? When you have individuals or have things that you read, that communication somewhere breaks down. So with that, I'm going to share with you my experiences, and there's going to be 4 different areas where I think communication is important in what I do. Communication with myself, communication with my students, the communication with my colleagues, and also the communication with mathematics itself, primarily through texts, papers, anything that you read that someone has written, but you can't talk to them, they're talking to you, but then you talk to yourself about them. So those are the 4 areas that I would like to actually discuss in my presentation. So when it comes to communicating with yourself, myself, that is, I do reflect a lot and I do talk to myself, and I think it's really healthy, especially in this day and age, to just be disconnected from all information that comes to us and just really have that authentic moment and think about what you're doing, where you're going, how are you, interacting with other people. I think it's really important, and a lot of people, I think, miss out on that. And so I do reflect a lot about myself, and I'm pretty down and negative on myself. I'm really hard on myself. Some of you probably won't see it because maybe we're not that close, and that's okay. But in my personal time, when I'm in my own thoughts, I really do criticize everything that I do. More importantly, say that I have a bad lecture, and it happens quite often with me. Sometimes I'm human, I can only do so much. I make a calculation error, right? Or I explain something and it isn't the most clearest way that I could have presented this mathematical concept to students. So yes, I take time after class and I think about what have I done, right? Can I fix that mistake? And maybe I'll go post the corrected solution on the learning management system, or come next class and say, well, listen, I messed up on that number, and, the calculation went a little sideways. Or the next time I teach the course, can I take a different angle to actually explain that particular concept? And I do actually think about these things quite routinely. Most of my life is thinking about my work, believe it or not. But also I'm reflecting about myself, and I actually did this yesterday, believe it or not, with all of my math courses. What I like to do is give this anonymous Google form for students to fill out. Okay, there's no grades associated with it, so you can probably see the response rate is, you probably think that the response rate is not that big, and it's not. There's no credit, there's no carrot for them to fill it out. But I really do appreciate that student who actually takes the time to answer that Google form. And there's only 4 simple questions. What can I continue doing in the course that makes your learning, experience, good? What can I improve in the course? And what can I stop? What should I completely just, that's enough. I've had enough of it. It's not working for me. And I also ask the students to reflect upon what they can improve so that they can succeed in the course. And the responses that I get from that, I do read them, and I try to, fix myself, fix the course, and reflect upon the things that I make, the choices that I make in the course, and the way that I teach, and how I communicate with others. So sometimes I'll give you an example. So one student said in one of my courses that I'm way too fast when I speak, that I should reduce it by 20 to 25%, that I need to give students time to take it in and reflect about whatever was being said in an example, or a definition that I've just explained, or a concept, whatever it is. And so that's great. It's a good reminder for me that I do probably speak fast, and maybe I'm speaking fast right now. I'm going to try to slow down. I'm reminding myself too. So that's good to get that type of feedback, and I do consider it. Sometimes when it comes to my lectures, students, another comment that came through, the concepts, or the examples that I do in class are too trivial, that I should do more harder questions that are similar on the test. That is great. But what is hard? What is like similar to the test, right? What's that reference? How do you make that metric? So, this question's harder than this one. What is that? If I see that students are struggling with basic ideas and they can't grasp, say, like medium level questions, I can't really always jump into the deep end automatically. I have to start from the shallow end of the pool and slowly tread to the deep end. I can't just have everyone drown. So I think about that too. And I think it's really good to get information from students to see how you are communicating to them and what they are actually receiving from you. So that is when I reflect. Now let's move on to students. Okay. So the communication that I have with my students. Okay. So sometimes what I've been noticing through my short career in the teaching and learning of mathematics at a university level, I've noticed that sometimes it's not the math that is really bogging them down. I feel that it's just, them not being able to, access certain information, or having the right direction to, channel to. Sometimes it's also personal things. Something is happening in their lives, and it's, impeding them in their learning. But when it comes to, accessing information about the course, like when is the assessment? What should I know for the assessment? What's coming up? One of my favorite things to do with students, and students, some of them do appreciate it and they enjoy it. And it's my way to lighten up the mood in the course too. At the end of every week, I have something called a weekly wrap up. Okay, so I'll just give you a breakdown of what it is. So I say hello to the students in a different language every week, and some students pick up on that and like, oh, you said it in my native tongue. Hello, and that's very nice. They connect that way, and I'm slowly trying to break down the barrier of our course being this ordeal. But so I'm trying to be inviting and friendly, and trying to get to their level, and so that they see that I'm also human, and I want to really reach out, and and I have them, and I want them to succeed in the course. So after that, there is a quote, an inspirational, it could be from Buddha, Confucius, some pop culture reference, hopefully, that they will understand, to motivate them to continue on in the course. And then after that, I have their tasks. I tell them, okay, so you have this term test, it's on this day and whatnot, and then provide a link where to get more information just in case you missed the announcement about the term test and its information. You have this link here that you can look at. And then what happened in class this past week and what to experience in the upcoming week. And you can read upon that if you wish. And then after that, if they got that far, they might come to an LPT. For those who follow Reddit, it's a life pro tip. Some little antidote for them to, think about how they can succeed in their studies and life. Sometimes it's just go on the nature walk on my campus, just to like clear your mind and then come back to your studies. Or, just to remind them to keep at it, to go to lectures, tutorials, and just to show up, because it actually does do something for yourself if you actually are present. Even if you didn't understand anything, something might click down the road. So there's that little antidote. And then at the end, my favorite thing, the signature of this weekly wrap up. Even if there's 30 people that are on the teaching team and I'm coordinating the course, I have everyone's name listed. I think teaching assistants are really important. I try to be as inclusive as possible. And now there's an emoji or two that is filled in that weekly wrap up. But students really appreciate that. They see that like I care, that I'm trying to reach their level, that I'm trying to understand them. And with that, hopefully I'm able to like draw them into the course and to try to do some of the math in the course, and to actually see that it's not, that bad, and they can actually succeed, and they can have all that support from us, the teaching team, and so forth. So that is something that I like to do, just to get them on the same page, but it's hard to get everyone on the same page. As I said, there's a multitude of reasons why students don't connect with us in our math courses. It could be personal, it could be whatever that hinders them to be present with the mathematics. So another way I like to communicate with students when it comes to teaching, I like using mnemonics. I'm sorry, I do. And I know that there's individuals that say, oh, English is not the first language of some of your students. You have a diverse group of students. They might not know the reference of that little mantra that you say in class. But I found that for myself, I like making them, and it does help students to remember certain mathematical concepts and certain routines. And this really comes from a different space outside of my professional life. The mnemonics, the mantras. I used to practice yoga religiously for about 10 years. Hot yoga was like my second job at one point. And then I got an adult job, and then I couldn't fit that in. It was great. But I remember being in class, they constantly said these things, and some of them actually stuck with me even to this day. So these little sayings, just, how to be in a posture, what to think about, how to like push through. And my favorite one, the saying that was constantly said was, when you want to get out of that pose, that's when the pose begins. And I thought that was very powerful. That moment that you just want to say enough, I want to get out of it, I just want to leave this situation. I think that's when the situation actually, brings upon a lot of interesting things. So imagine me telling my students, when you want to give up on that math problem, that's when the math begins. It would be a very fun time. I don't think the students would react very well to that. But that's the reason why I do these mnemonics. It helps me to remember things in my everyday life, little benchmarkers from my yoga time. And then also when it comes to mathematics, I have these sayings where say that you want to take the derivative of y equals some expression of x that ln takes on. So y equals, say, ln 2x, right? And so the way that I instruct the students to think about taking the derivative of this ln expression is, okay, so 2x, that's ugly, right? Ln 2x, oof, that's really ugly. So to take the derivative of it, I would say 1 over the ugly, right? times the derivative of the ugly. And so just by saying that, somehow it clicks with them, you know, that is how I take the derivative of ln. Or if they have to like take the derivative or integrate an exponential function, I say, oh, that's such an egotistical function, e to the x, oh, egotistical, so vain. It likes to show up in the result of differentiation integration, its original self. And then the other part is just to do the differentiation or integration after. So if you just write it out in its vain self, you got half the question possibly correct. You have to do a little bit more. So the reason why I say that I think this works, I have a funny story to share. One of my former students, so just after COVID, I had an opportunity through the Academic Skills Center to create these just-in-time, you know, meetups, if you will, at my campus. And so my former student, he was running it, and he was talking to this one student, and sure, maybe wasn't this just before a moment where they're discussing mathematics, but mathematics was being discussed. And the student goes to my former student saying, oh, is that like when the graph smiles and frowns? And then my former student's like, you were taught by Andie. So what I meant by what the student meant by smiling and frowning, they remembered what concavity is, like what's concave up and concave down. So if you draw like, you know, two eyes, and if you see that, you know, the graph of the function is smiling, that's concave up. And then if you draw another two eyes and, you know, it's frowning, that's concave down. And somewhere in between, there could be a mood change, which is the inflection point. And so these little things, it just lightens up the mathematics. I know that, you know, I'm taking away the formal structure and this rigor to it and everything, but you have to sometimes understand who your audience is. Maybe they're just taking that one math course, one and done, because they're in life sciences, and that's all that they want to do with math. And it's unfortunate. I'm sorry, Peter. I know I feel you sometimes when it comes to certain students, but it is what it is, and I'm just trying to get it so that they can get through the course and, you know, succeed. So that is something that I like to do, is mnemonics. And I actually wrote a paper about that, and it was a good old time. So the third thing that I wanted to talk about is communication with my colleagues. So some of it was somewhat mentioned in the introduction about myself. So the communication about communication with my colleagues. So I'm going to talk outside of my department. I don't want to stir the pot. But so mostly the spaces that I help run and organize, I really do enjoy doing that work. I don't know, I get some, some sick drive out of it. And it really pumps me up to see people are coming together with like-minded interests and whatnot. So, being in that space, organizing. So as you know, probably, you know, if you're with someone, being on that same page and organizing something with one person, it's hard. If you have a handful of people, it's harder. And now imagine having a community to think about. It's very hard. So there's a couple of spaces that I'm a part of, which were mentioned, and I'm very grateful to be a part of that, because I've learned a lot through these spaces, you know, how people, you know, run their courses, design their courses, assessments, and work with their students, and any other outreach and research that they do. It's just pretty amazing to be a part of these spaces. And I think it's important and healthy to have these places for people to share and communicate their ideas. So FYMSiC, first year math and stats in Canada, is one space. So FYMSiC, first year math and stats. What is my time? Sorry, I don't know when I start. Plenty of time. 11:15. Okay, so stretch. Okay. Okay, so we'll stretch. So FYMSiC is one place, first year math and stats in Canada. It started in 2018, believe it or not. The inaugural event of FYMSiC was here in this room. So it was during a MathEd forum, April 2018. So FYMSiC started with Miroslav Lovric, who's one of the co-founders, and Veselin Jungic from Simon Fraser University. And so they had this, vision to bring university instructors together, because it was missing at that time. There wasn't this space where university instructors can come together and just, talk about their experiences. Primarily at that time was first year math courses, any first year math course. So that has been around until now, 2025, so about 7 or so years now. So it's still kicking. We've had 2 in-person conferences, and hopefully you'll come to the 3rd one, which is next year in May. Just a little plug from the 7th, the 8th at McMaster University. It will be a grand old time to see everyone in the flesh. A lot of us have probably just met online, so it'd be great to, come together and just have these authentic conversation in person. So when it comes to FYMSiC, there's different places for people to communicate and share their ideas, one of which I've already mentioned is the conference, the in-person conference. We also have online teaching meetups, which happen 3 to 4 times per a semester. Maybe not in the summer so much these days, people are busy. But fall and winter, you can guarantee that we have these online teaching meetups where we have individuals come and present their work. Sometimes it's a panel, sometimes it's just a general discussion around the water cooler. But it's great to have these, type of gatherings throughout the term so that people actually feel that there is a space for them to go and share their, experiences when it comes to teaching and learning of mathematics. And so these online meetups, they have various themes. They sometimes don't hit everyone's interest, and that's okay. It's really hard to get everyone on the same page. But if you do have a moment, come check us out. Charles gave a great presentation on Thursday about Breda, so that was very nice. Thank you very much, Charles. And so that's one other space that you can participate in. The newsletter. We have this wonderful newsletter where you can contribute. And from time to time, we get these wonderful pieces of like the work that people have done within their classroom, or it's something outside of the classroom, some outreach. So it's a wonderful, fantastic place. We have several hundred people actually read that newsletter. So it's a great moment. So if you're interested in publishing something and getting the word out, we have a big, strong community of over 700 individuals, which is pretty amazing. I'm pretty proud of that. That is a fantastic place. So to run FYMSiC, there's a lot of behind the scenes stuff, which I like doing. I get this like sick kick out of it, if you will. And it's not enough just to, put in your calendar, oh, on this day, I have to email out the community to do something. No, there's also, you have to have vision, you have to have planning, you have to get people on the same page to work together. So that's probably what I like doing. We've been successful for the past 7 years. It's been great. And I hope that many more years to come will be for FYMSiC to continue on the path that we're on. Another space that I'm a part of, which I'm very grateful for, thanks to Brian Forrest. The CMS, the Canadian Mathematical Society Education Committee, I've been on that for about 5 years now, more specifically on the Meetings Oversight Committee. So that is a wonderful place. So anything education for any meeting, be it in person or online, please come to the online version, the MathEd meeting. It's happening in November, so this is another plug. You can present if you wish. The presentation deadline is October 2nd. So please do that. It's a great space. And so anything when it comes to math education at a meeting, my committee, together, we collectively think about who to invite as an ed plenary. Diana will be the head, plenary this winter meeting. So she's a superstar, rock star. And so it's just a great space to shape all the things that happen at in-person and online meetings through the CMS. And there's other spaces too that I'm a part of. I'm a pretty busy person. I've been appointed to be a board member for the National Numeracy Network. It's this US-based community of practice. So I'm a part of that, and I help organize their annual conferences and any other events and items that they are trying to bring people together on. So that is a fantastic space as well. We don't have a numeracy group like that here in Canada, unfortunately. And since I'm a part of numeracy, it's a great space to connect with like-minded individuals in the US. And lastly, at the Fields Institute, I'm a co-director of the Center for Mathematics Education. So I'm very grateful to be a part of that space where I get to connect with all types of individuals who are engaging with mathematics. It's a wonderful place, and I hope to make that space also fruitful for future endeavors that we may pursue. So communicating with colleagues, it's really hard to get people to come together and be that vital force, and you need that momentum. And for me, I think it fits the bill for what I like and my interests, trying to get people to come together. And it's hard. I'm not always the most liked individual in the room, or so it's hard to be that person even when the chips are down, and to support others. But I do enjoy it. It is my little guilty pleasure of being a part of all these spaces. So yeah. So another space, my last space, and I have a lot more time. That's amazing. Okay. So what happens if my talk is a little bit less than 50 minutes? Am I going to be? Okay. It'll be okay. Okay, great. Okay, fantastic. I wrote it down all on paper. I did my talk, and I didn't want to have flashy presentation slides. Lately, I've been noticing that individuals have these polished presentation slides, if you know what my quotes may mean, and I have to read the slide, I have to listen to the person. I would just rather that I can hear one's thoughts, and them being authentic and fleshing out their ideas. I think that would be great. But sometimes you do need a slide to show a graph, an equation, and whatnot. But I purposely wanted to do it old school instead of having presentation slides. So the last way of communicating for me, when it comes to mathematics, the bulk of my research is looking at math texts. And so for any course, what is this central place where people would probably go to if they don't come to class to read upon math in a course? What would that central place be? I was talking so much, I apologize. So what would that central place be? It would be the textbook, right? We all have that textbook that we can refer to if we miss class, or if we need extra, support and understanding that mathematical concept, or to practice, examples and exercises from and whatnot. And so some of my research has been in looking at how mathematics is being communicated through textbooks, papers. What are people saying? And so through this, I've noticed that the way that mathematics is sometimes being presented written, that there might be some confusion, some ambiguity, and so forth. And so I've done some work with some of my colleagues, just looking at various mathematical concepts, how it is being explained. So one paper that I'll discuss is on geometric limits, where myself and Kai Andrie and Miroslav Lovric have looked at the Ontario high school math curriculum, as well as math textbooks in the high school level. And we wanted to focus on how are limits at infinity being explained in textbooks. A lot of times through the textbooks that we've read, when it comes to speaking about limits, you're asked to use your intuition, right? Use your intuition as to what the limit will be as the limit goes to infinity, right? And so is intuition sometimes enough? So sometimes you have your gut feeling about something, but is your gut feeling always correct? And the answer is probably not. So sometimes it could lead to false conclusions as to what something is if you just solely rely on your intuition. And so I'm going to use the chalkboard. I feel that these days in my life, dinosaur technology is most reliable. So I'm just going to go to the chalkboard. This was planned. I'll present a couple of ideas that we've actually thought about in that paper. So intuition, does it actually help us to understand certain mathematical concepts? So the very first idea that I'm going to present that we discussed in the paper is, say that you have a rectangle, and this rectangle has infinitely many lines, okay? So I'm drawing a rectangle, okay? Pretend there's I can't do infinitely many. We live in a finite world, okay? And then you have a parallelogram, right? It has infinitely many lines as well. Now, the rectangle and the parallelogram have the same height. Okay? And same base length. And so you ask your students, is the area of the rectangle and the parallelogram the same? Okay, so think about it. Just using what I've given you, okay? You have this rectangle and there's infinitely many lines that create that rectangle. And you have this parallelogram and there's infinitely many lines that create that parallelogram. And they both have the same height. They both have the same base length. Is the area the same? So what if a student asked you, how would you explain that? So think about it. Yes, Diana?
I know they are, but like it looks like the area of those things is longer, you're stretched. But like the best explanation that I've heard is actually someone took it down and like held it up like that, twisted it, and it's like, yeah, you get infinite lines like changing length when they do that, and shifting in line and everything. But yeah, it is intuition kind of tells you that it shouldn't be.
Exactly. Someone else, did you have your hand? No, sorry. Yeah, it's not that easy, exactly. And so intuition would say that, oh, yes, sir. Mhm.
Is we start talking in different places. So you're not getting the same thing. Doing the why.
Exactly. So as you can see from, yes, Miroslav. Sorry.
Okay, I have all these vertical lines in the window there. And then these two lines alone, I put all of them together, get another figure. So, where I kind of sort of combination this equation as you don't know the area space that's high. That's translation. So how to do somebody that reasons like that? You know, now, make it look so good, right? How would you explain this to somebody who's I don't think problems in it.
Sure.
Again, manipulate intuition, draw by diagonal all the rectangle. Have another color. Put them in there, have them wrap around and call it.
No, this is all great. As you can see, it's not very easy. It's not a trivial thing, especially, yes, sir. Oh, sorry.
Well, you can just say that if you have a lot of cards, like in Diana's case, it's not, the top is not straight. It's like really, really frilly. And yeah, anyway, I don't know if that helps, but.
Since I got the mic, can I add one?
Sure.
So if you take the second diagram and you make it very skewed, one of the things that I think will kind of become visible is that it actually gets thinner visibly, and that might help with the intuition.
So as we've all seen different ways to think about this, it is rather challenging for someone who is like 14 years old and hasn't really dealt with like working with infinity and whatnot. But as Diana said, the area is the same between the rectangle and the parallelogram. I mean, the area of a rectangle and parallelogram, which comes much later, is base times height, right? But reasoning when it comes to having, infinitely many lines to explain that these two areas are the same might be very challenging for some students. And intuition on its own, just by looking at the visual, you can't always rely on that because it could lead to false conclusions. A student might say, oh, these lines are longer. And so, the area of the parallelogram must be bigger than the rectangle, but it's not the case. They're actually both the same in terms of area if they have the same height and base. And so we looked upon this one particular classic example. So how do you derive the area of a disk, right? So say that you take this disk and it's centered and has radius r. Okay, how do you derive the area of a disk? So what you could do is, and this is a classic example in many textbooks, is you can cut it up into wedges, so into pizza slices, if you will, and you connect the pizza slices, pardon my drawings, okay, you can connect the pizza slices, okay? And so what happens here? So one would say, well, it looks like, you can create this parallelogram out of it, right? And so the area of this would be approximately pi r times r. So the area would be pi r squared, right? But then what happens in some of the textbooks, they say that, well, if you take infinitely many wedges, what happens, right? So if you take infinitely many wedges, you cut these pizza slices even further and you have smaller pizza slices, what happens is, eventually, if textbooks say, all of the ones that we have read, that the top and the bottom flatten out, right? The top and bottom flatten out and you get a rectangle. But I would say, do they really flatten out? If you had a microscope that could really zoom in to the top, what would actually be there? Under the microscope, you'd still see the arches of some of the wedges being connected. So it doesn't really flatten out. So this idea of limits and having things go to infinity, right? Taking infinitely many wedges and trying to see what happens. I think that what the best thing that we can say is that, no, it's not the area of the rectangle. It's approximately the area of a rectangle in this particular case. And that we should be looking at snapshots, because limits, it's a process, right? It's a dynamical thing. It's not this final, object that you are trying to reach to, okay? It is approaching to something, yes, the final object, right? In the limit, the final object, what will it be? The parallelogram would actually become close to a rectangle. And so this idea of limits when it comes to explaining in textbooks is a little murky in some textbooks. And imagine a student reading this in high school about limits and trying to wrap around their finite experience into something that is infinite. And it doesn't always translate that intuition is going to be the correct answer, as you saw in this particular example, the first one that I've mentioned. So reading textbooks and reading papers, I think it's really important to ask, what is the author trying to communicate? And now authors, sometimes they want to present the material in a very friendly way so that the student or whoever is reading it, they can digest it and it's easier for them to understand a particular mathematical concept. Another idea, a part of my research just recently with Miroslav Lavrik, Veselin Jungic, and myself, we wrote a paper about how continuity is discussed in calculus textbooks, okay? So in that paper, we first begin discussing limits, right? And most of you, if you've taken a first year calculus, if it was of the Stewart flavor, probably were using limits and you're plugging and chugging, trying to find that final answer, or the limit doesn't exist, right? And so most textbooks, most students would take that Stewart type calculus, if you will, if there's no proofs involved. they would just do that plugging and chugging. It's almost like they're treating the limit as like a function. You just feed it a number and then out comes a number. But it's not. It's this process. The limit is this process. How close are you getting to something? What is the distance from one thing to the other? There we discussed limits. But then sometimes in these textbooks, these calculus textbooks that we looked at, the precise definition of a limit is in another section or at the end of the book. It's not really thrown into the discussion, the general discussion about limits. And so I feel that that sometimes disadvantages students, because then all this language starts popping up once you go down calculus, on an open interval, on an open disk, it contains this point AB. All this language pops up. And I think that if students were possibly introduced to what a limit is, right, and these ideas of like, how the distance between two objects and approaching some object, I think some of the later language might actually make sense to students. So when it comes to continuity, okay, what is typically said in textbooks, a function is, I'm going to write CONT, continuous, at point A if the limit as x approaches a of the function f of x equals f at a. So most of you probably saw this in your first year calculus course as the definition of continuity. And then shortly after, authors say there are three conditions that must hold. So condition number one is that the function at a is defined, okay? Number two, the limit exists. And last but not least, the limit as x approaches a, f at x equals f at a. Okay, so this is generally what is presented in most, calculus textbooks, those who are not doing calculus with a proof flavor, but are learning about limits. And so there's a lot that's happening here. There's a lot that needs to be unpacked. But then shortly after this, what happens is, authors say that if one of these three conditions doesn't work, okay, the function is not continuous at that point. It's actually discontinuous, right? So if one of these three conditions fails, right, then the function is said to be discontinuous, okay? And so what we did in the paper, we examined two functions, f of x equals ln x and g of x equals 1 over x, right? And what we said was that, okay, so let's take f of x equals ln x and say that we want to talk about whether or not the function f of x is continuous at x equals, say, minus 10. That doesn't make any sense because, okay, what are the values that ln takes on? What are the values? What is the domain of the function? The domain of ln x is positive values of x. Okay, so x being greater than or equal to 0. So it makes no sense to talk about some value of x that's not even in the domain of the function or even close to the function, right? So some textbooks would mention this particular example that we've investigated. And then when we looked at g of x 1 over x, the reciprocal function, pardon my drawings, I'm not Desmos, but I'm trying my best. So in this case, again, they would look at, okay, so what happens when a equals 0, right? What happens when a equals 0? Again, g of x is not continuous at a equals 0, it's discontinuous at a equals 0, right? And so in this case, to some degree, it's a little bit better than this situation because there is some action happening around, a equals 0, right? You can talk about the behavior to the left and the right of x equals a, okay? And so understand what the function is doing. So there is discussion about these two particular functions. More importantly, when they talk about what does it mean to be discontinuous at a point for a function? I have to use another board. I'll lift this one up. Can this go up? I still want that, and I have to raise the other one. more importantly, what happens is all this language starts popping up that students probably did not experience if they were just being taught limits with a plug and chug type mentality. So when it comes to, discontinuity, how is it thought of? So I'm going to write out the definition by Stewart. Okay, so if F is defined near A. Now this is pretty loaded. If F is defined near A, what do they mean by defined near A if they've never actually played with it and they were taught limits just by plugging and chugging? What does defined near A mean? So defined means that there is an open interval that contains A. So there's an open interval that contains A. And what does it mean near A, right? So the distance, okay, in this case, say that F depends on X, the value X is trying to get close to A. The distance between A, X and A is getting smaller, right? But not zero, right? So what does it mean to be smaller? How small, right, is the question. So there's a lot that is being said in this particular statement that sometimes we just kind of gloss over of the way that we actually present limits. So if F is defined near A, okay, F is said to be discontinuous near A if F is not continuous at A, okay? So that was the definition of what discontinuous is when you look at Stewart's textbook. There's a lot that's happening here. The beginning of my statement, if F is defined near A, okay? And what does it mean by discontinuous? After that, it's usually classified that the function is discontinuous. It could be removable. It could be a jump discontinuity and infinite discontinuity, but they never really explain it through limits, what is actually going on. They do show graphs, but what does it mean if you do have a jump, if you do have an infinite or removable discontinuity? And there's actually another discontinuity that doesn't get mentioned quite often in textbooks, is an essential discontinuity. So it's like a removable discontinuity. I will show you an example. So it is like a removable discontinuity. So you have sine, say, pi over x, okay? So if you want to evaluate this function, f of x equals sine of pi over x at x equals 0, you have a little bit of a problem, just a slight one. So around the, I can't draw it, around the y-axis, the graph is oscillating, right? And you can't really predict what will it be exactly at x equals a. As you get close to, x equals 0. As you get close to x equals 0, I mean, it could be 1, it could be -1, as you get closer and closer to the value of x equals 0 because of this oscillation. So this would be considered as an essential discontinuity, in that I can't redefine this function to give it a condition to make the actual function continuous. And so sometimes this particular discontinuity is actually being left out, and only 3 are being mentioned. So there are a lot of issues in how continuity is being presented, and it probably stems a little bit from how, or a lot from how limits are introduced, that it's not just this thing that you plug and chug. There's a lot going on, and that some language starts to appear that if they had, maybe the understanding of a limit through the epsilon delta version, the definition of the limit, the language might be a bit clearer. And then the situation in my second year calculus courses even gets worse, especially when we talk about mixed partials. They equal one another. So if you have second order mixed partials that they can equal one another, the order in which you take the derivative doesn't matter. The theorem states that suppose a function is defined on an open disk that contains this point AB, and the mixed partials are continuous at this point AB, then we can say that the second order mixed partials equal one another. But what does it mean to have this open disk all of a sudden? And then you have this point in the open disk AB. What does that all mean? Especially if you're just teaching, second year calculus, where it's just an extension of something that they've seen in first year through a version of calculus from a book by Stewart or alike textbooks. So that has been something that I've been very interested in, looking at how mathematics is being communicated by the author, and how students might perceive misconceptions, and how ideas might be a little bit ambiguous. And sometimes, as I said earlier, the author wants to present the idea in a user-friendly way because of the audience that they're speaking to. But there are details sometimes swept under the rug, again, for the user-friendly version. And when you do teach these math courses, I mean, you do have to worry about who your audience is. You're not going to possibly teach a calculus version with proofs in it to life science students because they might not need it. But it would be really great to know where certain things come from and the language that we use to express ideas when it comes to various mathematical concepts. So I have other ideas, hopefully in the future, that I will continue on looking at how mathematics is being discussed in papers and textbooks. It's coming, some of which is going to be published soon, which I'm pretty excited about. But I think communicating mathematics is really important so that the audience understands and can digest the information. So communication, I think it's very vital. I think it's very important for us when we think about any relationship, but more importantly, when it comes to mathematics, I think the way that we express it has to be clear and concise. And so that is pretty much the ballpark of what I do in my time when it comes to the teaching and learning of mathematics. And so I will conclude my presentation and thank the fields once again. Thank you for coming, everyone, and thanks for all those people that have been supporting me over the years to come to this point. So thank you very much.
We had a question online. Pam, would you be able to unmute for the online question? Oh, it's in the chat.
Yes, let me see. Kate, would you like to, you had an excellent question about the limits and whatnot. So would you like to unmute and ask your question?
Sure. Can you hear me okay? Yeah, lovely. Hello, everyone, and congratulations on your award. It's lovely to see your success. It's been a while since we saw each other. I did have a question about areas. So when you were talking about the example with rectangle and parallelogram, and you were relating on the intuition of students, it sounded like we already assumed that it has. And I wonder, have you looked at how that intuition is particularly developed? Because what I've noticed is not every teacher is giving, for example, the area concept in the way that can be generalized and extensionalized, and then they understand that, for example, the areas can be moved and so on and so off. So I'm just curious if you considered looking at the texts of before the concepts are used, kind of thing.
Not really, no, we haven't. We just looked at what was being presented when it comes to looking at limits at infinity, in particular geometric limits in that paper. And so for that particular question, it was just to show that using your intuition, if you wanted to think about, if you take these lines and fill in the rectangle, call it whatever you will in our mathematical language, it's area, that filled in space, is it the same as the filled in space in the parallelogram? So that was just to illustrate that your intuition, your gut feeling, by just looking at what is visually in front of you might be misleading, might lead to false conclusions, right? So it was just to bring up that point that intuition possibly is not going to give you the correct answer, that it's not enough to just go by that.
Let me just extend my question, maybe
Sure.
I just formulated it a little bit wrong. have you looked just at one book, or have you noticed that just some authors do a little bit more this walk away into the intuition, or they all kind of just like based on that? Like, are there different authors and different perspectives with respect to even on Calculus 1 and the limits, just based on the intuition? Or you just looked at the stewards kind of thing?
We were looking at high school textbooks here in Ontario, how it's being discussed when it comes to geometrics and limits at infinity. We have several examples in that paper that we actually have seen throughout the math textbooks, but the one about the rectangle and the parallelogram, it was just to bring up the idea that intuition solely is not enough.
Maybe you lost me at some point when you talked about the limits, but were all the definitions and explanations kind of like around the same, or were there any different ones?
There are variations.
Okay.
When we looked at the four examples that we discussed in the paper, one of which is being the formulation of the disk formula, there are variations between textbooks. They're not all the same, but I hope I've answered your question.
Yeah, no, that was lovely. Thank you.
So I'm just wondering, Howard, would you like to unmute or? Okay.
I want to be in there too. So what three concepts do you want your students to take away from your calc course and your teacher's course that they'll use throughout their lives and careers?
What three concepts does that?
Three basic concepts.
Mathematical concepts?
Mathematical concepts.
That's a good one. Three mathematical concepts that I want my students to take away. I'd have to think about that. Okay, I would have to think of. Okay, yeah, I would have to think about what that would be. If there's like three main mathematical concepts that I want my students to know, that's a good one. I'll have to get back to you after lunch.
All right. Thank you very much, Andie.
Thank you.